Nat is a wonderful designer. When you meet Nat, you can see him crunching through the thought process design as he watches you play test his games. Nat has used his background in aerospace engineering. Yes, we have an aerospace engineer who designed board games talking about today. We are happy to have for our board game career seminar, Nat Levan. That's it, right? Levan.
All right, that's it. I'm good.
And he's going to talk to you how you can also use engineering skills to help with your projects, to help your design, specifically board game design. That show is yours.
Thanks, guys, for showing up. I'm glad to see they brought me with pizza. That always works for me. I'm here today to talk to you about overthinking in your design. Overthinking, generally not regarded as a good thing. You know, it's often, oh, don't overthink it. But it can really be helpful, and I'm going to tell you a little bit about why. First, who am I? I got my bachelor's in aerospace engineering at Virginia Tech in 2006. Right now, I've been at the same company for about 10 years. It's a really small company, about 30, 35 people. We do engineering services, which means basically everything from design through testing, through making drawings, to even doing some manufacturing. That's my first job out of college, and it's been a long 11 years, but a good 11 years. What we do is we focus on mostly high-performance composites. That's stuff like fiberglass, carbon fiber. If you follow tennis at all, Serena Williams just won her latest Grand Slam using a tennis racket that we helped manufacture. So even though we're a pretty small company, we have our hands in a lot of big things. Who am I as a gamer? I've really only been into board games for about 7 years now. It doesn't seem like that long to me, but it goes, it actually starts to seem like a long time when I put it in those terms. I've started game design for about 5 years now. I've got a couple games, New Bedford, Nantucket Time Management from Dice Haiti Games. I've got a game called One Card Wonder that should be coming out later this year. I do a whole bunch of really tiny games that fit on hopefully one card or just a couple cards with a couple bits, mostly for promotional stuff. But I've been doing a lot of those. I've been writing about game design since 2013 on my blog as Overthiinking. I'm going to talk a little bit about what overthinking means when we apply it to design. I'm going to talk about how engineering and game design are related. That's going to be the meat of this presentation. I'm going to look at some of how that overlaps and some specific engineering tools that you might be able to use, not just for game design, but just generally. Why is overthinking actually a good thing? Because you need to be smarter than all the people that you are giving the design to. If you weren't, they wouldn't need to pay you. Simply solving a problem is not enough. It's not enough to say, all right, here's the answer. Because things go wrong. They go wrong all the time. Because you need to solve everything that's going to pop up after you hand off your solution to the problem. And that often means answering questions before anybody knows that they need to ask it. I do that all the time. I get up from my desk, I go to see someone to talk about something that I've done. I get halfway there and I turn around and say, oh, you know what? He's going to ask me about this aspect, and I don't have an answer if he asks that. And so I go back to my desk, sit, work for another half an hour, and say, okay, now I'm ready to go. A little bit more detail on game design here. Bernard Suits had this kind of long quote about what a game actually is, and then summed it up very nicely as the voluntary attempt to overcome unnecessary obstacles. That means a game is an artificial problem. You wouldn't be playing a game, solving the problems in the game, if the game didn't exist. It is problem solving. So when you're designing a game, you are designing problems for other people to solve. Something kind of similar happens in engineering. Scott Adams, you know, as the creator of Dilbert, engineers like to solve problems. If there are no problems handily available, they will create their own problems. That is definitely true, but engineering is also solving problems. Anytime you solve a problem in engineering, you're uncovering more problems. The goal is to get rid of all the problems that you're going to cause before you cause them. And finally, good design solves problems before anyone knows they existed. And I said that just now. That's the first time it's been said. Please take notes. Every time you're working on a design, you're definitely going to run into problems. Engineering trains you to anticipate a lot of these problems. And it gives you a lot of tools that help prevent and avoid those problems before they happen. What do I do day to day as an engineer? It's a lot of sitting at a computer. But there are 5 main tasks that I'm doing while I'm sitting at that computer. And I do bits and pieces of these probably 4 out of 5 days a week. And the last day I try and take it easy. But I start with modeling, analysis, testing, project management, and reporting. A little bit more about each of these tasks that I do during the day. Modeling. You're basically given, here's something that you need to create, here's a problem we've got, we need a solution. Sometimes it also involves making it physically. Sometimes the two don't line up. You know how you want to represent something, you know how you want to make something, and you can't do both at the same time. So you got to find ways of working around it. Analysis, you typically have a solution, and you have to either convince somebody that it works or explain to them why it did. That can be sometimes an even more important job than explaining why something works, is explaining why it didn't work. Just saying yes and no, it does or doesn't, usually doesn't cut it. Testing. You have an actual thing that you need to demonstrate that it works, or sometimes demonstrate that it breaks when you expect it to break. Engineers love breaking things. That is one of our favorite things that we do all the time. I have coworkers who literally just sit in the back and break stuff 8 hours a day. But that's often an artificial environment. You don't know exactly how it's going to work out in the field, work when it's actually used by a consumer. And so you need to take what you've learned in testing and apply that to something bigger. When you're doing reporting, I'm sure you guys have all written reports, but it gets tougher when you get to trying to explain how you solve these problems, because you need to say not just what we did and here's what you need to know, but you need to include enough to recreate the work in the future most of the time. You need to prove that the work that you did is valid work. Again, that's all in order to get paid. If you just give someone a sheet that says, yeah, this is good, and walk off, they're going to say, well, I don't believe any of this at all. We're not going to sign the paycheck, and that's a problem. You really kind of want to get rid of as much vagueness as possible when you're doing that sort of thing. Usually, sometimes you need to be a little bit sneaky with your words so that you don't back yourself into the corner. We like to call that wordsmithing. Finally, project management. And this is kind of the catch-all, that you're answering all the questions that everybody could possibly want to ask you so that when you hand this off, they can't come back and say, all right, well, now you need to do more work, but we're not paying you any more money because you should have already done this. And so you really just need to have every contingency and every problem out of the way before they happen. In game design, there are several basically parallel disciplines to what I do as an engineer, which works out really nicely. The modeling, the early stage, that's the concept development of your game. Analysis, you're working at development and continuing and proving that everything works. Testing is play testing. Reporting, your report for a board game or a game is your rule book. How are people going to be using this? Making sure they've got enough in that rule book to know that they can actually play the game that you've designed. And the project management is kind of publishing side, because you need to make sure all these things line up before you pay someone a lot of money to go print something on cardboard. So you really want to make sure that works. So I'll start with model creation. Nothing ever behaves how it does in the real world. And the whole point of modeling something is to understand what's going to happen before it happens. But it's always a simulation, and so you're going to have to make some compromises in your level of detail. That means you've got different assumptions, approximations, and abstractions that you're going to have to take bits and pieces out so that you still have enough to get the answer you want, but not so much that you can't actually get it done in the time and level of effort that you want to put in. This is one of the places that my engineering education comes in on a day-to-day basis. How do I take different real-world scenarios and apply them to this 3D geometry? Because you've got a car driving over a bridge. You can't just say, okay, well, put a car over this bridge and show me how it happens. You have to take into account all these different aspects of how the bridge is, what the foundations are, how the car is actually moving over the bridge, how the wheels of the car interact with the bridge. And so which of these are actually going to matter to get the answer I want, which is this bridge going to fall down? And hopefully that answer is going to be no. But it's a similar action when you take a look at the game and decide what kind of mechanics and behaviors you want to happen in the game. You can't, if you're designing a game about the French Revolution, you can't put in every single event of the French Revolution. You're going to have to pull bits and pieces from it and just focus on the ones that you want to represent. If you do a game about whaling, for instance, you can't capture the entire 100-year history of the whaling industry in America. You have to say, all right, I want these specific parts of it, and everything else I'm just going to kind of represent with a couple cards and a couple bits and pieces. How do you do overthinking when you're doing model creation? That's when you sit down and look at, are these abstractions reasonable? That's one of the most important questions you can ask yourself. Are all my assumptions reasonable? Because it's okay to just say, all right, well, I'm going to do it this way. But you actually want to come back later and say, all right, here's why I did it this way, and this is why I can actually believe the answer that I got when I made that assumption. Flexibility of design. This is something that comes in usually pretty early in the process, because you're going to change things a lot when you're starting out a design. The easier you can make that on yourself, the better it is. And so you can spend a little time overthinking at the beginning, and hopefully that's going to avoid wasting time later. When I'm working on making a model, sometimes I prefer to do a little bit more work to prepare something when I know that I'm going to need to change how big something is. And thinking ahead on those can really be a time saver for me in my day-to-day. The same thing in games, that usually applies to your prototype. If you're making your prototype, there are a lot of ways, a lot of tools for making sure that when you go back and say, all right, these 3 parts here didn't work. How can I swap them out? How can I change things without having to basically completely redesign, produce this prototype? There's a whole bunch of tools for that, both in engineering and game design. We can go into those in a little detail if anyone has interest, but for right now, just highlight some of the online platforms, a couple programs like NAMDEC. But that means that if you've got a game, I've got 2 games right now. One's got 100 unique cards in it, and I've got another one that's just got 15 unique cards. It sounds like the 100 unique cards would be a whole lot more difficult to make than the 15 unique cards, but by using some of these tools to merge data from spreadsheets, it actually ends up being a whole lot easier to make the 100 card game, because the 15 card game, I have to do each one of those by hand. You want to overthink this by planning for all the changes you think you might need to make. If you don't make change in the end, you've only wasted a little bit of time. But if you have to go back and redo the whole thing from scratch because you didn't plan for it, that's going to be wasting a lot of your time. Of course, this can get out of hand. From our favorite webcomic, XKCD, every time you automate something, it seems like a good idea, and the more you go in, you find out, well, okay, now you just gotta do this one thing to make it more general. Oh, no, wait a minute, now I gotta develop this a little bit more, and so you can go overboard on that. As an example, there are at least 2 other XKCD comics that cover the exact same subject, so yeah, efficiency is good. Next topic, avoiding edge cases. Edge cases, that's pretty much anywhere that things interact badly in unexpected ways and the whole system breaks down. Finding these in code is debugging it, things where you think you know how it's going to work, and then first time out of the gate, something crops up that nobody expected. In my job as an engineer, as a structural engineer, this often means avoiding kind of artificial elements, things like sharp corners, which don't exist in the real world, but absolutely exist in a computer. Or if you can't completely get rid of them, at least confining them to somewhere that you can hide them later. You can try and rule out the obvious problems first. In games, that's stuff like infinite loops, naive strategies where you just do the same thing over and over again. Those are things you don't want to have ruining your game. But even though they're not the intent or the overall process of playing, most of the work that you do when you're designing is going to be avoiding these unique one-off cases. But I will highlight an example from a pretty popular game from it was 9 years ago, Dominion, which is a card game. And it turns out that in the base game, there is a single strategy that wins something like 75% of the games by just buying money. And it completely ignores the entire point of the game, which is buying all these other cards that do things. So they kind of defeated the purpose of their own game by having this edge case pop up. They did fix that eventually by releasing more cards, fixing the original version, but that was kind of a big error at the time. Fortunately, it didn't hold the game back, and it's done quite well. How are you going to overthink avoiding edge cases? Really, you just want to make fewer small problems for yourself. Anywhere that you can eliminate these unique details, that's going to help avoid these edge cases. Because it gives fewer places for these things that you don't expect to interact. Estimating unknowns. Sometimes you're working on something. I do a lot of work with material properties, how strong something is, how hard it is. Sometimes you just have to assume a starting point. You don't know exactly what the value is going to be, but you have to just start somewhere. Ideally, you're always going to calculate everything from the start, and it's just not possible all the time. In games, that's especially problematic early on in development, especially when you're talking about games with a lot of interaction between players, and especially games that have a lot of economic aspects, like auctions. You know, there's just no way to calculate how a lot of these things are going to work out exactly. But it's useful to know the range of values sometimes, your best case and worst case scenarios. Really, the same thing comes into play when you want to make sure that no player can run away with the game or have an easy victory. And I'm going to come back to this a little bit later with some specific ways to get around this. You can always get around it with doing a whole lot of play testing. And sometimes you're going to need to do a lot of that play testing anyway. But the whole point here is that by doing some of this overthinking, you can start with these estimates, do the math, and save a lot of those playtests, save a lot of that time. Sensitivity and stability. You know, sometimes you're not really looking for a specific answer on something. You're looking for more of an understanding of how the system operates as a whole. The previous slide, estimating, that's more of what we call a static approach. It's not really something that changes over time. Take a look at it at a fixed point in time. Whereas the sensitivity and stability of a system is much more of a dynamic approach. You want to know how it changes across time. Looking at it in just one slice is not going to give you that understanding. What this means is you want to know how things happen when you change a value up or down by 10%, or a factor of 2, or a factor of a half. You're basically varying things systematically so that you can understand how changes in the overall system come out of these little changes. If you see big changes in the overall system, you might have to go back and do a little more work to tighten those up. And if you've got a small changes in the big system, then you know you've got a pretty robust and responsive system. I encountered this a lot when I was testing on Bethany. I had a condition of probably right before going to publish it, or going to Kickstarter to get funds for it the first time, where I was worried that one of the two main strategies in the game, one of them was going to be too important and you could just ignore the other one to play the game. And I didn't really know which one it was, but I was afraid that after a year and a half of playing this, I'd missed something completely. Fortunately, I had a lot of data that I could go back to. I recorded scores, I had logged games, and I started working through the numbers by saying, all right, well, what if these things here, what if these whales are worth twice as many points as they are? How does that change the outcome of the game? Okay, well, that's good. It doesn't really change it that much. Well, what happens if all these buildings are way off? Okay, well, good. That doesn't change it that much either. And so that kind of gave me the confidence that when you're playing the game, you weren't going to run into a situation where one of these things was the obvious route and you just ignore half the game. I had a pretty stable system there. And that's really the point of overthinking this, is that you want to be sure that you're not going to break down when it's in use over time. You want to know how it responds in the long run. For testing and play testing, one of the things that we do a lot is iterative solution. When you're approaching a new system, there's a whole bunch of complex issues. There's any one of 100 things that can go wrong at any given time, and that really makes it tough to troubleshoot. What I do when I make models at work, I basically start with a shakedown model, which is basically as simple as I can make it that still operates roughly and has the properties that I want it to do. The same thing happens when I make a board game. You kind of get to that very first version that shows the behavior you want it to show. It's sometimes called the fail early approach. But, you want to get that game to the table as fast as you can, and then as you go on in engineering or game design, you're kind of layering additional things in and adding that complexity one piece at a time, so that as soon as something stops working, you can point at it and say, this is the thing that made it stop working. And that's really valuable if you can highlight those as you go along, isolating the sources of problems and solving them one by one, rather than trying to solve everything all at once. I have that problem in a game that I'm working on right now called Statistical, and working in that has kind of sucked because things that I'm really concerned about in it, which are long-term strategy, the flow of the game, balance, I can't really test those until I've got all of my details in place, because because of the way the whole system is set up. Anytime I encounter an exploit, that's going to disrupt the entire results of the testing. So I'm kind of doing all this work, and I'm not sure that the game works in the long run. But by going through step by step and adding in these things one at a time, I'm at least shortening that work that I don't have to redesign the game from scratch each time I hit a problem. At the bottom here, I've got versions roughly 4 through 9 of another game I'm working on called Iceberg, as in Pittsburgh. But I don't even have the first 3 versions anymore, but you can definitely see step by step here. There were bits and pieces that I could save each time and carry them over to the next version. Statistical significance is probably something I didn't encounter until I started working in engineering. One data point is not really enough. When we're doing testing at work, we've got 2 types of tests, really. There's a screening test, and there's a characterization test. So when we're trying to choose material, we might want to look at 5 different materials, and for each of those, we're going to do just a handful of tests so that we know which one we want to work with. But when we go to actually use that material and sell the product, that doesn't cut it for the person who's buying it. And so we take the material that we've chosen and go back and do a much more thorough and robust set of tests, the characterization tests, so that we can point to this and say, look, all this data, we know that 99% of the time, values are exactly what they say they will be, and the rest of the time they're within 5% of it. So you can be confident, we can be confident that what we say works still works. When you're going through and designing a game, that often means that the farther you get in development, the more tests you need between changes. When you're early on in the development cycle, 1 or 2 data points might be enough to tell you this whole part of the game is not working at all. I can get rid of it. I can do something else. Once you get close to publication, you're going to need to really have a lot more data behind you than just, well, this didn't work in 1 test. Well, was that 1 test because the players didn't understand? Were they new players? Was there something else? Did you change a small rule? Were you trying something out? That having more tests gives you more confidence that you can ignore some of these anomalies and these outlier data. I have an article on my blog about red threads. And the point of the article is basically, everyone knows red flag, not good. When you're doing tests, when you're looking at data, look for the red threads that, if one person says something and that's the last you hear of it, you don't have to worry about it. If one person says something that's kind of related to it and someone else says something that they don't like it and a third person says, well, they don't really understand why that was there, all of a sudden these red threads come together and they make a red flag. On a playtest recently, we were playing another designer's game, and we had an argument break out because we ran into something that was a rare occurrence, we were told, and how rare was the sticking point of the argument. Because they were guessing it might happen in 1 of 100 games, which does not seem like a lot, but when you're selling 2,000 copies of a game, that means that the first time out of the box, 20 people are going to have that happen. And not just those 20 people, but all the people they're playing with. If these people play it 5 times, all of a sudden you're getting to a large percentage of people who have played your game who have run into this problem. And that's not rare. When you're doing your reporting, when you're doing your rulebook writing, clear communication is absolutely critical. I've run into so many problems in work and in game design because I was not communicating clearly enough. Things you can do to help is define your terms, then use them. Don't switch back and forth. Don't call something the discard here. Don't call it the trash there. Don't call it a sink. Don't call it your used cards. Pick one of those terms. People are going to be looking for any place they can to discredit you. In business, that means that they're looking for a reason they don't have to pay you because you haven't done the work that they asked you to. Even if you've done the work, if you don't explain and prove to them that you've done the work, they're not going to pay you. In games, people are looking for any way that they can to use loopholes to their own advantage. You have to assume some amount of effort on the part of players. Picture I've got here at the bottom, you don't have to define how to roll dice. But, for anything that you're doing which is unique, which is new, be as clear and complete as possible. I write a ton of reports. Sometimes it seems like I'm writing more reports than I'm doing actual engineering, math, or modeling. But it's always important to list your assumptions. You can't just say, here's what we did. You need to explain why you did A and not B, and explain the good reasoning behind it. How many of you guys are game players at all? Handful. How many of you have played a game and you get kind of halfway through and the person explaining the rules says, oh, here's something I forgot to mention. Yeah, that sucks, right? So, be kind to game teachers. I've taught enough games that I've made that mistake plenty of times. We also do our best. And when you're designing, sometimes you're so deep in it, you don't really know that you're doing something that you do automatically, even if you don't mention it specifically. And for that, you have to be your own rules lawyer. Look at every rule and try and figure out how you can bend it as far as you can without breaking it. That still would be technically within the rules of the game, because players are definitely going to do that. Online message boards are full of questions saying, hey, I did this because the rules didn't tell me I couldn't. And that's really disheartening to hear as a designer. This is something else I run into all the time when I'm writing reports, because I'm sending reports not just to my boss who knows what I'm talking about, but he's sending it to someone at the customer side who mostly knows what I'm talking about. And frequently they're showing it to their boss who doesn't really have any idea what I'm talking about. And so when you're going through all these different levels of reporting and people handing off your document, some people are going to pick it up, they're going to read the words, make sure it says what you think, and ignore everything that's in the pictures. Sometimes you're going to have people that look it up, they find the chart that they want. Ah, great, here's the this table, here's this plot. This picture shows me exactly what I need. And in big words under the picture, you can write, this picture is not to scale, and that's not going to matter. Of course, Magritte's famous pipe. This is not a pipe. Of course it's not a pipe, it's a picture of a pipe. But some people are going to look at this and say, all right, this is trying to tell me this is a pipe. The words right under it tell you it's not a pipe. Make sure your words and your pictures agree. Even if you know why they agree, somebody looking at this might not understand that. How you can overthink this, do your show and tell, redundancy, redundancy, redundancy. In rulebooks, people use rulebooks in two main ways. They use them to learn the game, and then they use them as a reference later. When you write as a way of learning the game, it's important to have it laid out clearly, but when you use it as a reference, you don't know exactly where people are going to look for your data or your explanations. So when you have it in there multiple times, it increases the chance that they're going to get it right. Closing in now on the end of this section with management and publishing. Integrated design. When you're designing a product for sale, I think this is something that a lot of people don't fully consider. My company is so small that we have to take on every part of this from an engineering aspect. You know, we have to be the ones, I have to know personally what's going to go on in the lab when they test it. I have to know what's going to go on at the manufacturer when they make it. I have to know what's going on when they ship their product out and somebody tries to install it, and then when they actually finally use it at the end of the day. I have to know how the guy is going to draw the pictures to explain to the shop how to make the thing. I have to understand who's paying for all this and how we get paid at the end. And you need to consider pretty much all of these connections when you're working through the design, because no part of the design exists in a vacuum. On the board game side, I'm the designer, and there's a couple steps away from me to get to the customer. But yet, I've got to consider all these different aspects when I'm working on a design. I've got my game design, and I've got kind of a sense for art, probably. I'm going to translate those things to the publisher, who's hopefully going to translate them to the customer. The customer, they're often going to be pulled in by art. So how you put art, how the publisher does art, that's going to directly affect how they present it to the customer. The publisher is going to take the design, and they're going to work on putting it into production, which means they've got to interface with the manufacturer. I need to know how they're going to work with the manufacturer to put it into production. That means I need to understand what they're going to do with components. And the components lead directly into how much the manufacturer or the publisher is going to be able to charge for the game. If I go to a publisher and I say, I've got this great game, it's got about 900 cards in it and 40 different dice that are all custom, even if it's a great game, no publisher is going to touch that because it's way too expensive to put on the market. On the other end of that, I do a lot of games for promotional stuff, and I try and get them to fit on 1 card, 2 cards, standard size playing cards. And that's about as cheap as you can produce a game. And even so, that means that the cost, instead of being less important, it's even more important because the margins are so thin on this. I'm talking to a publisher I'm working with right now about a game that fits on, I guess it comes with 3 cards and a tiny little sheet of tokens. And he's saying, man, last month we gave away your thing and we charged $4 for it because it had 3 cards and 8 tokens in it. But these couple extra tokens, or a couple extra cards, all of a sudden we might need to push this to $5 or $6 just to make it worth our while to do this at all. And so, thinking ahead to what that's going to be at all steps of development and sales, there's nowhere to hide that in a game that fits on 1 card. Finally, consider your end use. You've got to think about how people are actually going to be using this when they get it. Sometimes people do this intentionally, sometimes they do it accidentally. From the designer point of view, it doesn't matter whether it was intentional or accidental. You want to make it as easy as possible for people to use things the way that you intended it to be used. You want to know not just what the right way to use something is, but what the wrong way to use something is too. Because enough people see this, somebody's going to use it the wrong way. So you need to kind of correct for that in the design process. That's how I ended up with adding components and parts for a solo game when I designed New Bedford. So you can play that just by yourself and have an experience that's similar to the rest of the game when you're playing with other people. Because I was looking around, and at the time, everybody online was saying, this is a great game. How can I play it if I don't have anyone around? And a lot of things were popping up online that weren't from the designer. And it was, here's one I made for this other game that so that I could play it by myself. And I knew that if that was going to happen, that was something I wanted to make happen. We spend a lot of time designing things and trying to avoid people making mistakes. Instead, it's much better to allow for repairs after mistakes have been made. This happens in physical stuff and stuff that I engineer. We're making parts that are pretty big, and they take them out and they put them on a boat, and they lift them up on a crane, and they kind of slam it into the side of the boat, and all of a sudden it's not exactly the same shape that we wanted it to be. Or they put a little hole in a piece of it. And so we need to make sure that when we're designing, if they put a little hole in, we can come back, we can fix that hole. If they bend it out of shape, it's still going to work, and we have ways of fixing things. I want to talk a little bit about a couple specific tools. I can run through these pretty quickly that I use as an engineer that also apply to game design. Damage-tolerant design. That's really related to what I was just saying about putting holes in things. Design your product to break a little bit without failing completely. You want to avoid a single point of failure. When I'm designing a part that goes on a boat, don't have it all depend on a single bolt that's working. You want to know that if that bolt goes, the rest of the structure is still going to work the way you intended it. In a board game, is there a single die roll at the end? Is there a single critical action that completely, that the game will hinge on completely? For some game weights, that's a good thing, and you might be okay with that. For other games, if you're playing a 3-hour game and it turns out an hour and a half into it that you have no way to recover from where you are, you're not going to enjoy the remaining hour and a half, and the people you're playing with probably won't either if you let them know. A term that's thrown around in my industry a lot is PLM, Product Lifecycle Management. Basically, it's the idea that you're designing something for its end of life. A lot of the parts I make for boats, they go out on a boat, they're out there for 30 years, and then they're going to come in. So we need to make sure that they're strong when they come in after 30 years or longer, and they're not necessarily going to be just as strong as when you send them out, but they still meet all the requirements. Enveloping. This is something that we often try to use when we're debugging things that won't work in engineering. When you can't predict it exactly, try and establish the boundaries. You can say, well, I don't know exactly how big this is going to get. I don't know exactly how strong this is going to need to be. I don't know exactly how big of a load this is going to be. But you can make those estimates and try and say, well, this is the worst case scenario. This is the best case scenario. And you're basically defining this region in the middle between the two lines of here's where it could possibly be. When I did this for New Bedford, I took a look at some of the key strategies, the simplest strategies in it, and said, all right, what happens if a player takes the same action spot and uses it as optimally as possible? Every turn, they use it as much as possible. And I had a spreadsheet, and I basically worked out turn by turn what they would have at the end of the game. And it came out to 23 points. Did it with another building. It came out to 24 points. And when I played enough games, I was seeing that a good score for winning is going to be 24 points or more. And so that tells me that, okay, even best case scenario, my envelope for using these single actions, which is less fun and something I don't want players to do, that envelope, even though I don't know exactly how they're going to use it in the game, it's still below what I want people to actually do. That's the same reason that I got rid of a building, a way to get points for having more money in the game, because you could, when I worked that math out, you could definitely get way more points with that than you could doing what I wanted players to do. Even though I didn't know exactly how many points, I knew how many they could get, and that was enough. One of the things I do most often in my job is global local modeling. It's kind of a question of scale. You can't always model in infinite detail. If I'm working on a boat, I can't look at every thread of every bolt on it. I can't look at every fiber when we're making fiberglass. But through global local modeling, you basically start with the big version of it, which is kind of rough, and as you go down, you get more refined, more detailed versions that only cover a very small area. And then you can translate what you learned from the big part to the little part, analyze the little part, and then translate those results back up to the big part. So you don't have to do everything at once. You can break it down. A lot of times I balance a game by looking at what an average turn will get you. And so I don't necessarily need to see how that average turn fits into the whole game, as long as I can make sure that what happens on an average turn meets my expectations. And at the same time, I can look at what happens in the overall game without needing to know what happens in the details of all those turns. Last topic I wanted to cover is reproducibility. It's not enough just to know that something can be done, because it's really hard to prove that something can't be done a lot of the time. You really want to understand when something goes wrong, how it happened, so you can either do it again or prevent it from happening in the future. When you're writing rules for a game, there was a famous game a couple years ago called A Few Acres of Snow about the War of 1812, I think. No, French and Indian War. And basically, there was one path in the game where if you take about 10 specific actions, you were guaranteed to win. And there's no way to write a rule against taking those 10 specific actions. Because someone could get to the 9th action and say, well, no, I'm not going to do the 10th action, so I'm not violating the rule. And if you forbid someone from taking any of those actions in order, you've kind of limited an entire section of the game. So it's really important to understand the circumstances when something goes right and when it goes, as much as when it goes wrong. Identify any systematic issues that can happen in the future. I've done tests where we ran the tests and values came back way less than we were predicting them to be. This testing happened down at West Virginia University. And basically we went back and said, okay, I think we understand now. We weren't capturing a really important piece of this when we did our work. And so when we do capture that, we actually match up pretty well. Without being able to go back and match that up, we would have been in a lot of trouble. This also affects replayability of your game, which is usually something you want to shoot for. You want somebody not to just play it once and then feel like they never have to play it again. If it's something that somebody can do over and over again in the game, reliably, you got to watch for that. It might be something that breaks the game if they can do it, or it might be something that you do want them to be able to do in multiple games no matter what happens. Always end with conclusions. Or put your conclusions at the front, but that doesn't work as well for a presentation. But you want people to know why you've done all the work that you've done. So let me review what overthinking is. It's having the answers to your questions before you have the questions. It's multi-layered problem solving. You're predicting problems, you're solving them before they happen, and you're designing in a way that can minimize these problems later. What that means is it's basically a way of exercising control. As a designer, once it leaves your hands, you have no control over it. And so in order to get paid for it, you need to make sure that you've got all these things locked down. I just answered a question last week about my game Bethany. Somebody thought there was something that might be overpowered, but I could run through basically the exact calculations showing someone that it wasn't overpowered. It worked the way I expected it to be. And that's because I've done all this work up front and done the overthinking, and I knew before that it left my hands that that wasn't an issue. How does that apply to game design? Remember that designing a game is creating problems. Whenever you create problems, you're going to run into more problems. When you're playing a game, you're solving problems that somebody created, and that, again, often creates more problems. Games like to layer in all these problems on top of each other to create complexity. So you're really solving problems that, when you're doing game design, you're solving problems that were created by the players because they were solving problems that you designed them to solve. So anytime you can try and avoid problems with your thinking and improve ways for players to run into problems, you're helping your design. And overthinking your design before you ship it out helps solve them at all these different levels. Overthinking at a design stage is good. The more problems you solve ahead of time, the better your product is. Because you get paid to be smart. When you're an engineer, when you're a game designer, pretty much whatever you choose to do, you're going to be paid to be the person with the answers. And time thinking is almost always cheaper than time actually doing something. And so you can think of that as the more time you spend thinking, the more time you're getting paid.